All right, this is number 7, 1.3 topic question. Number 7. I'm going to solve this one twice. The first way is a simple way, but the simple way is not simple unless you memorize an equation. So in case you didn't memorize the equation, we'll solve it without using the equation that I recommended you memorize. So here's the system. We have a car at initial velocity. It slows down at a constant acceleration, so my acceleration vector must be opposing my motion so that I come to a stop. It travels a distance delta x in a certain amount of time t to do that. And if you look at the multiple choice options, what we're really doing is we're trying to find VO, what's its initial velocity, but in terms of, because of the multiple choice options, in terms of delta x and t. There's a simple way to do this. The simplest way to do this is to remember the following. This is not on the equation sheet. If A is constant throughout some time t, throughout, excuse the poor spelling, but we'll use shortcuts, right? If A is constant throughout some time t, then throughout that time t, or for that time t, my average velocity is just going to be 1/2 my my final velocity plus my initial. So it could be v plus v naught. Of course, you could memorize the other situation, the v naught plus v. It doesn't really matter. It's just a sum. And those are vector quantities. So this is my average velocity along a certain vector direction would be those vector components added together and then just half of that. Okay? That can be derived if seeing the derivation and all that helps you remember or believe this, let me know. So if that's the case, but we also know, right, that there is a definition of average velocity. It's the non-derivative. It's this good old slope calculation. That thing is, this is also true no matter what. The average velocity is just delta x over t. So if you remember these equations, or remember that equation, then this is a definition. But if you remember that equation, then therefore delta x over t has to equal 1/2 v plus v naught. And for this system, my v is 0, and you're home free. Okay, v naught's equal to 2 delta x over t. All right, what if you don't remember that equation? What are you going to do? All right, well, we'll use this as an opportunity to just talk through or think through general kinematics. So if you don't remember that equation, the ones you're equipped with are the following. And I'm going to drop the little x subscript because it's just this dimension. Okay, so we're always working in this dimension, so I'm not going to specify it. So my final velocity is just v naught plus at because we're in constant acceleration. So these equations off the equation sheet work. I have x equals x naught plus v naught t plus 1/2 at squared. Now, I don't have x naught explicitly. I've got, this is initial position, final position, right? But if my initial position is 0, then then my final position is my displacement. So I can rewrite this as delta x is just equal to v naught t plus 1/2 at squared. There's that third v squared equation, but since we know we need to find this in terms of time, I'm not looking for anything timeless. I actually want to keep time in there, so I'm not going to write the third equation. Okay, the only thing that's different between the general equations and our system is that our final velocity is 0. So to help my brain out, I'm going to rewrite these with a 0 final velocity and taking advantage of delta x. Actually, I'll do that here. So these two go together, right? So if I think of this one, I can get to this because of that delta x. If I think of this one, because this is 0, then I get that my v naught is equal, v naught 0 is equal to v naught plus at. 0 equals v naught plus a t. Okay, so what are we trying to find? V naught in terms of delta x and t. So I'm going to grab these two because now these two forms have been customized to match this picture, right? To match what I've got here and the fact that my velocity is 0. So I'm just going to write them both out again to help my brain see what's going on. Delta x is equal to v naught t plus 1/2 at squared. And I have that 0 is equal to v naught plus at. Now, the other thing I know is that a, if I'm going to think of v naught as a positive, right, or if this direction is positive, I know already that a's got to be negative. So whatever the magnitude of a is, I could factor that in here. Or in other words, if I think of this a, because these are numbers, and I could factor in the direction information already. So, for example, in this equation, that's got to be v naught minus at, because as time goes on, time progresses forward. If I know my acceleration, the magnitude of my acceleration, that's got to be a negative sign, otherwise I'd never get to 0, right? Because this keeps growing as the product of a number, a scalar a times t, increases, and the only way that sum is going to go to 0 is if this is negative. So I could rewrite this as, I know 0 is equal to v naught minus at. Keeping in mind that a now, if I suppose I had numbers, if I had to solve for a, I would expect a to be positive, right? Because I took care of the direction already. Okay, so I'm going to write the same thing here. Delta x is equal to v naught t minus 1/2 at squared. I've got delta x, I've got t's in here. So this one looks really simple, so I'm just going to write this one out. V naught is equal to at. Oh, at, v naught. So I'm going to write that in. Notice when we arrange, when we do math, we're going to keep building up this habit. Equations, you kind of build downward, and then if there's an in-between, so if I want to show that I'm doing this, and then I want to use this thing over here, help the reader by giving some space, It's just a clue that maybe you're working these two down, then you see this, now you're going to take that and factor it in. You can also draw arrows and things like that, but for now, I'm going to leave a little gap here where so you could tell that I'm going to use this guy. So delta x is now equal to at times t minus 1/2 at squared. Well, delta x is just at squared minus 1/2 at squared, which is just 1/2 at squared. Okay, right? That looks pretty good. But what's a? Well, I don't want to use that. Well, what about over here? This is going to help kind of factor that in already. So if I divide, let's try this. Delta x is equal to 1/2 at squared. But that's, if I multiply, let's get rid of the half. 2 delta x has to equal at squared. I'm so close, but I want v naught in terms of delta x and t. So I've got a t there. I need to get rid of the a. So how can we get rid of the a? Well, over here I've got at. It's funny because I've got at here. That's almost, oh, wait a minute. That's equal to at times t. That's just equal to v naught times t, right? Because this is v naught, and there's t. So 2 delta x equals v naught times t, home free. V naught is equal to 2 delta x over t. So there is a way to get to that answer. Whoops. There is a way to get to that answer. Am I off the screen? I might be off the screen. Lost it right here. But there you go. There's a way to get to that answer without remembering that 1/2 V plus V naught equation. All right, that's number 7.